start off today, as we're starting off, I want you guys to work on heat equation problems worksheet number 1. I mentioned at the end of class yesterday, you might have done like one problem, but you didn't really have much time to work on. Go ahead and get cooking on these. We're going to do a practice one here together in a minute, and then we're going to talk about this lab. So go ahead and get cooking on this. Yeah, and we'll do something together here shortly. Yeah. Why don't we do this first one together? This is number 4, which is at the bottom of this worksheet. Let's talk about this one together to get a little warm up. Okay, so how much heat energy is required to warm 275 grams of water from 76 degrees Celsius up to 87? Okay. Alrighty, so when I'm first assessing this, let's see here, Mr. Patak! What variable is it even asking me for? You think it's Q? Why do you think that?
No. Really? Realistically?
Intuition. Or something to it. He's right, it is Q. What lets you know it's Q? Oh, goodness. I'm dying. Ms. Schmidt? Okay, yep. It's asking for heat energy, and that's definitely a Q. So that means we must be given, in some way, the M, the C, and the delta T. It's the only way we can figure this out. All right, well, if I'm breaking this down, my M, my mass, 275. My delta T, Mr. Lee, do I use 76 or 87 for my delta T? Which one of these temperatures do I use? There's 2 of them. Uh-huh. So whatever should I use for my delta T? Somebody tell me what it is. Stencil? 11. 87 minus 76. You're using 11 for your delta T. Every now and then someone's going to try to sneak a 76 or an 87 into there. Watch out. It's the difference, the change in temperature. All right. And then, let's see here. John, my C. I use this number.
4.18.
Oh, wait. How do you know that?
That's specific capacity of water.
It's water! 4.18, 4.18, 4.18. Don't you forget! Don't sleep on that 4.18.
I didn't forget. I just concealed water.
Don't sleep on water, son. Unless it's a water bed. Right? Oh, man, that was good. I know Jones liked that one. All right, sweet. Anyways, you plug all this hot mess in. Boom. 0.5. There you go. And of course, I'm a model student, so I'm putting a box around my final answer. And now, yes, ma'am. Oh, I totally should. Look at you, smarty pants. All right, so why don't you guys try? Be cooking on 5 and 6. Those are on the back of that worksheet. See what you can come up with. So get cooking. We might talk about one or two of these here in a minute. Alrighty, well, with this one right here, I'm looking at this. I'm just going to do the setup. I'm not going to finish it off. A quantity of water is heated from 25 to 36.4. It absorbs that many joules. What is the mass of the water? Well, if I'm setting this up, okay, remember Q equals, what is it? Q equals M. Yeah, MC delta T. Okay. Alright, so if I'm setting this up, well, I got a Q, that's 325 joules. My M is, I don't know. Because it says a quantity of water. I don't know how much water I have. Mr. Hall just called me a nerd again. Whatever, Hall! Alright, anyways. Boom, roasted. My C is what? My C is what? My C is 4.18! Because it's water! Water, 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 water. Alright, anyways.
And also what?
There are times at restaurants where I'll order some water and they'll bring it to me and I'll like picture little molecules in there, the 4.18. Those are the kind of things my wife is like, yeah, don't share those with me. I don't want to know about that.
Did you know the density
Anyways. And then my delta T, okay, so delta T is my 36.4 minus 25, so we're looking at 11.4. All right. And I got to solve for this guy. So you guys can figure that out from this point. The answer key to this is on Schoology. It's in the Monday and Tuesday folder, I believe. It's in both, so you should be able to cook. Let's go ahead and talk about our lab today. We got a thinker today. Usually I'll give people this lab, and they'll be like, wait, what do I do with this lab? And I'll just be like, yes. I'll just make them figure it out. But it's a determination of the specific heat capacity of a bolt. Of a bolt. Let me sketch a little bit. I've been frying this bolt for a while here. For those of you at home, let's see here. I've got a little bolt. It's been in boiling water for like 20 minutes at this point, probably. So the temperature of this bowl is definitely what at this point?
100 degrees.
100 for sure. Okay. So here we go. I want to find the heat capacity, that is the C, of this bolt. Okay? Again, this bolt looks like this, by the way. Looks like one of these guys. Woo! Check it out, virtual. That's the bolt. That's in there. So I want to find the heat capacity of that bolt. Okay? Because I don't know what it is. So I'm going to do a little experiment. I'm going to fill out this chart. So I got the mass of the bolt. I got that. I wrote that down before you guys came in. And now what I'm going to do is, I'm going to get a cup. I'm going to fill it with water. I'm going to drop that bolt in. You can see how the temperature changes. Give me a good time. So mass of the empty cup right now, 0. 9.42. 9.42. Yeah, it's 2 cups because it makes it an even better insulator so we don't lose heat. Yep. And now I need to get about 60 milliliters of water. Now I'm going to show you guys something here. Sweet. All right. Mr. Pilcher did not measure this water super well, but it's close to 60. I got a quick question for you guys. How come it doesn't matter exactly how much water I have in terms of milliliters? Yeah, Kelsey? Yeah, I'm not comparing this to other stuff, so I don't have to have it be a constant. And there's another reason I'll show you guys here in a second. Hey, my initial temp is sitting at 22.7. Now here's truly why it doesn't matter, the amount of water, because I'm going to, for you at home, I'll turn this over so you can kind of see the scale a little bit. Yeah, here we go. I'm going to go ahead and plop this. There we go, on the scale. All right. So the mass of the cup and the water is 74.34. So cup and H2O equals 74.34. Now, if I want to find the mass of my about 60 milliliters of water, what can I do? Yeah, so if I have cup and water, if I subtract the mass of just the cup, which in this case was 9.42, someone plug that in for me. 64.92. So that must be the mass of my water, and that's why I didn't really care if I was exactly measuring out 60 milliliters, because I knew that I was going to find the exact mass of the water one way or the other. So whether it's a 63 or 59 or 64, as long as I know what it is, I'm okay, right? Because the Q equals MC delta T equation doesn't factor in volume, it just cares about the mass. So as long as I know the mass, we are good to go, okay? All right, so now what I'm going to do is I'm going to take this bolt, I'm going to plop it into the water and get that final temp. In she goes. Just going to get a little stirring around here. See what that final temp ends up being. It's climbing a little bit. We're climbing. Let's see here. Still climbing. Hike those patient pants up. Oh my. Oh, oh, no, it moved again. Looks like we're sitting at 27 point. Oh, there we go. Oh, oh. All right. So let me sort of break it down. I had this much water. I plopped the bolt with this mass into that water. We know where the water started temp-wise and where it went up to. We should be able to know where the bolt started at and went down to. And we see that the bolt, however much energy that bolt had, it made the temperature go up from here to here. Okay? So with just this information, you should actually be able to find out the heat capacity of the bolt. This is a tough question, by the way. I'll give you a little bit more guidance, and then I'm going to let you put you guys into the deep end here and see what we can do. So, some things I would like to mention. The heat gained by the water should be exactly equal to the heat lost by the bolt. Law of conservation of energy, right? So energy went from the bolt into the water. That amount of energy that the bolt lost should be identical to the energy that the water gained. So the Q of the tap water should be equal to the Q of the bolt. I'm going to see if you guys can figure this out. Some people will flounder. Some people will flourish. That's all right. I want you guys to have a shot at it. So, see if you can figure this out. Here's your data. Tell me what the C of that bolt is. I'll give you guys a few minutes. And you have no idea what to do, just try something. Put some numbers in and see what happens, okay? Give it a shot. Let's see if we can figure this puppy out. Okay. So the key idea I gave you is that the Q of the tap water is equal to the Q of the bolt. Another way to think of this is, so the bolt lost heat energy, right? Because it was the high temp when we put in the water. So the energy that the bolt lost should be identical to the energy that the water gained. So this is where we're going to get our Q, because a lot of people were starting with the bolt. They're like, okay, I don't know the C or the Q of the bolt. That's a problem. I need one of those two things. I think Millette, Wisconsin, she's like, I need the Q. Like, how am I supposed to do this without that Q? And so we're going to have to sort of work our way around, get that Q, and then we're on our way to the C. Okay, so here's where I'm going to start with this. So this is definitely be good things to write down. I'm not going to worry about the Q of the bolt at first, because I know I can't figure that out without my C. Okay? So the Q of the tap water, so Q equals MC delta T. So I know the mass of the tap water. I know the C of the tap water. And I know the delta T of the tap water. I hope you notice that I'm saying tap water a lot. I'm being very clear about what I'm talking about. So in this particular case, let's see what that was. So the mass of tap water was 64.92. So this is going to be 64.92 times 4.18. And my delta T was it 4.3?
Yeah.
Okay. 4.3. And I saw a lot of people with 4.3s, and that's great. 27 minus 22.7, 4.3. I like to see that 4.3. That was good. Okay? And we plug all this in. Can someone plug this in for me and tell me what they got? 1,100.
66.87.
Okay. Now that is this guy right here. That is heat gained by the water. That's how much heat went into the water. What's that?
It doesn't have to be negative because the bolt lost energy.
I see you're saying, okay. So this is a great conversation. This is why we talked about no negative Q's yesterday. So negative is just telling us the direction, whether it went in or out. And so instead of using negative, we just talk about direction. So this means that this is how much heat the water gained, and this is also how much heat the bolt lost. Okay? So if this is how much heat the water gained, okay, 1,166.87, that must be the same heat energy that the bolt just lost. And we're not going to worry about that negative symbol, okay, because we're already talking about the direction. We know it's lost heat, not gained heat. Okay, so we're going to use the Q of the tap because that should be equal to the Q of the bolt. Okay, so we're going to use the Q of the tap water. You guys see how the Q of the tap water should be equal to the Q of the bolt? Okay, so I'm going to use that 1166.87. Let's see here if I can do that over just a bit.
Dumb
board. There we go. Okay, now my mass of my bolt. Now again, before I was talking all water. When you're using Q equals mc delta T, make sure you use the same units every time. Water, 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 water. Q of water, M of water, C of water, delta T of water. So now that I'm talking about the bolt, Q of bolt, M of bolt, C of bolt, delta T of bolt. Okay? So here, if I'm going to plug these in, my mass of my bolt was what? 38.01. I don't know what the C is. And here's the last crucial step where a lot of people put in a 4.3. 4.3 is the delta T of the water, not the bolt. What is the delta T of the bolt? John?
73.
It's 73.
Yes, it's 73. Remember? Because the bolt started at 100 and it went down to 27, right? So the delta T of the bolt is 73. And if you were to plug this in, okay, so if I simplify this, where's my calculator? Here we go. 38.01 times 73. I got 277.4.73 times C. And that's equal to 1166.87. Okay? So what do I have to do to both sides? Divide it out, yep. So divide both sides by 277.4.73. 277.4.73. There goes that. There goes that. And whatever this value comes out to be is what your C is, which was what, Mr. Stowers?
0.42 joules per grams degrees Celsius.
Ooh, look at him dropping those units on there. Joules per grams degrees Celsius. The official heat capacity of this bolt, it's actually made out of iron. And the literature value, that is the officially accepted value of the heat capacity of bolt of iron, is 0.449. So that's pretty good data. That's pretty good data. We're right on top of there. Okay? So there are three things that you can choose to do at this time. Three things. Number one, I have some fake data here. You can try the same thing again with new data. Okay? So if you feel like, oh, I kind of got that, but not all the way, here's some brand new data, and your number should be about 0.449 if you did it correctly at the end. That's the first thing you can do. The second thing you can do is continue on your heat equation worksheet, number one, or the specific heat capacity bell work. Okay? So first thing is you can work on this fake data. Second thing is you can work on one of the worksheets in your packet that's practicing this. The third thing is you can work on your 3-question lecture quiz that's in the Tuesday folder right now. Okay? It is your choice which one of those guys you want to do. Obviously, the only one you have to do eventually is the 3-question lecture quiz. But that one's going to take some calculation. So it's up to you. We got 10 minutes. Get cooking either way.